Hi, it's me once again. So it's almost 2:21 a.m. So this is not anything related to you, but just my dissertation. I thought why not? I was not ready to say goodbye, so thought just practice the dissertation here. Just record the screen and post it here. So if any single one of you watching, so just let me know what I am doing now, what I can improve, and if you understand what I'm saying. So let's go. So good morning or good afternoon or good night everyone. My name is Subhajit and today I'll be presenting my dissertation topic, model-based approach to band gap theory, the Kronig-Penney model. This uh, this model explores how simple quantum models can help us understand the energy band formation in solid, which is very essential for modern electronics and material sciences. In quantum chemistry, electrons are just not particles, they behave like waves. When these electron wave travels through periodic potential in a crystal lattice, Um, they don't just move freely, they create allowed energy gaps and forbidden gaps. These band structures explains why some materials conduct electricity and others don't. To analyze this, we have to explore two very simplified and important model, Dirac Comb model and Kronig-Penney model. The main objective of the study was to understand how this periodic potential is able to affect the energies of electrons and the formation of band pair. Basically, I wanted to study and compare the Dirac Comb and Kronig-Penney model, then use Excel to stimulate energy band formations and solve the equation, draw some graphs, and compare the graphs to get the result and conclude some outcomes and to observe how parameters like band height, wide width affect the conductance and insulator properties of materials. So, to give you some perspectives, here is some perspectives. Early quantum models like Bohr's and de Broglie models help us to understand the discrete energy levels in atoms. Then comes Schrodinger, whose equation helps us to understand the behavior of particle in a 3D space. And here is the Bloch's theorem. Bloch gave us this equation, which describes how wave function behaves in periodic potential, leading to energy bands. This led us to foundation of band gap theory. Now, before going to the main topic, Kronig-Penney model, we have to understand the Dirac Comb model. Before understanding the real gas uh, or the van der Waals gas, we have to study and understand the real gas. It is very simplified. So, Dirac Comb model is very simplified and idealized model. It uses infinitely narrow delta function in a arranged in a periodically. This is expressed as Vx like this, where V0 is the strength of the potential and A is the periodic setting. You can see this is the Vx function and this is the A, the difference between two delta functions. Now to visualize the energy band structure of Dirac model, we solve this transcendental equation applying Bloch theorem and Schrodinger theorem. We get this main equation, which is cos qa is equal to cos k plus beta sin k. Here beta is this, A is this, and K is this, and Q is the Bloch wave vector. So this is a transcendental equation. So we cannot solve it numerically. We cannot solve this analytically. We have to solve it numerically. So in the left hand side is the function of z. So here the function of z is cos qa. We all know the maximum value of cos is +1 and the minimum value of cos is -1. So the value of right hand side should be within the region -1 and +1. The values outside the region of +1 and -1 and should be in the forbidden region. Now we have created a Fortran programming, this programming where we can from which we can get some result of conductance bands. You can see when beta is 1, these are the conductance band. You can see from 1.3 to 3.1 we can get conductance band. Then when beta is 5, when beta is 10, we can get that. I will explain this with the function with Excel with Excel. It is very simplified in there. So it is that programming. You can double check it in the same with this excellent Fortran program. So why this equation is continuous. So here cos QA is equal to Q pi 2 pi n by n. Since n is huge, the spacing between Q values becomes extremely small. As a result, the discrete allowed states are packed so densely within the energy band that they appear continuous. Now we get to the beta values, the different beta values. When beta is equal to 1, you can see the allowed gaps are increasing 1.83 to 2.6 to 2.83, and the forbidden gaps are decreasing. You can see 0.5 to 0.2 to 0.08. So more values are coming in the allowed region and less values are getting in the forbidden region with the increase subject. We get this curve. This graph behaves as metallic behavior. We can explain it in the next slide. We explain it in the next slide how. Now you can say when we increase the beta to 5, the here happens the same situation. The allowed gaps are increasing and the forbidden gaps are decreasing. When we change the beta to 10, it had happens the same thing. Allowed gaps are increasing and forbidden gaps are decreasing. But now here we have to notice that here the first allow gap is 0.85. But when we change the beta to 10, the first allowed gap is 0.51. So here the allowed gap is less and here the allowed gap is more. Now let's see in the forbidden band. In the forbidden zone, you can see the first forbidden difference 1.6, but here the forbidden difference is 2.1. Here the forbidden part is greater. You can also notice this in the graph. You can see in this part here is more in the more curve is in the forbidden region. Here the less part of the graph is in the forbidden region. So we can conclude that this is when beta is equal to 5, it behaves as semiconductor, but when beta is equal to 10, it behaves as insulator. So we can interpret from this graph that with the increase of potential state, the electron finds it hard to pass the delta potential. So electron faces resistance, band gaps widen and shift to the insulator behavior. Now, there are many limitations in Dirac Comb model, like mathematical idealization. There is no physical realism in Dirac Comb model, where here atoms are treated like points, which is not actually true. There is no concept of tunneling and barrier width. So, we don't use Dirac Comb as primary model. So, Dirac model is a great starting point, but it is highly idealized, so atoms are not really delta spike. So we move to the Kronig-Penney model, which uses finite width, square barriers, and wells. It is also capable of wave tunneling, barrier thickness, and wave interference. It is very flexible. We can change the well width, barrier width, and height to stimulate different material types. So Kronig-Penney model is very simple. Kronig-Penney model is divided into two unit parts, where one part is well region and another part is barrier region. We can represent it Vx. The Vx is equal to 0 when x lies between 0 to a. You can see this is a. So 0 to a, Vx is equal to 0. It is in the well region, but when Vx is equal to V0, the x should lie between minus b and 0. So these are the first expression of Kronig-Penney model. Then now solving Schrodinger equation in both the unit and applying Bloch theorem, we get this transcendental equation. This is the transcendental equation where k is equal to root over 2me by h cut, which is in the well region, and q is equal to root over 2m v0 minus e by h cut, which is in the barrier region. So it is the same kind of equation, transcendental equation, where you can see the left hand side is a function of z, which is cos kt, and we all know the maximum value of cos is +1 and the minimum value of cos is -1. So the value of the right hand side equation should be within the region +1 and -1. The value outside of the region +1 and -1 should be in the forbidden region. So now we using Excel, we numerically evaluated the right hand side of the dispersion equation for various values of E and different configuration of A, B, and V0. So when in the case one, when A is equal to 1, B is equal to 1, and V0 is equal to 0, you can see there are moderate number of energy bands, and the uh, the uh, the spacing between two bands are moderate. Then when we increase the A value to 2 and beta V value to 1 and V0 remains same to 100, you can see number of bands increases, and then and the spacing between the bands decreases. So it's morely behave like a metallic. You can see more energy bands. The spacing between energy bands is less, so it behaves as metallic behavior. But when we change the A value to 1 and beta value is equal to 2 and V0 remains 100, you can see the number of energy bands decreases, and the distance between two energy gaps or another energy gaps increases. So it behaves as insulator. So to summarize all these things in perspectives, we can say that increasing the well width A, the electrons more give electrons get full freedom, more freedom, so more band gaps appears. But with the increase of barrier width B, the tunnelings becomes harder, so more the difference between band gaps increases. This is so Dirac Comb model is great for mathematical understanding, but Kronig-Penney let us the understand the real world materials. So here are some application of Kronig-Penney model. It is very important for education purposes and nanotechnology, where electron flow at nanoscales. Now, it is also important for quantum well design, controls energy state in devices like lasers, LED, and solar cells, like infrared diffraction. It is also important for semiconductor engineering, basis for material and properties. KP model is also important for understanding the energy band gaps. Now, in conclusion, we can say that both the material demonstrate how periodic potential causes energy band formation. But Dirac Comb is very mathematically idealized and simplified model, but Kronig-Penney is more realistic and flexible model, which helps us explain the phenomena like real band gap tunneling. Through stimulation and analysis, I was able to visualize how electron behaves in a periodic system and how quantum mechanics directly explain the model electronics. These are these are some references I have used to get this to explain these models and for my study purposes. And lastly, I want to express my sincere gratitude to Dr. Dash, under whose guidance and supervision I was able to successfully complete this dissertation. I am also deeply thankful to all the teachers of Department of Chemistry whose teachings and encouragement have supported me throughout the academic journey. So, thank you. 13 মিনিট অলরেডি এখন হয়ে গেল, তো আমাকে 10 থেকে 12 মিনিটের মধ্যে কমপ্লিট করতে হবে। যাই হোক, জানি না কতটা কি বোঝাতে পারলাম। মোটামুটি যতটা পেরেছি করছি, এখনো রেডি নেই। জাস্ট এটুকুই বলার। ভাবছিলাম যে কি আর করি, এটা বলেই দিই, বলে দিলাম দেখ তোরা কতটা কি বুঝতে পেরেছিস জানাস। এটাই হয়তো লাস্ট, আগের ভিডিওতে গুড বাই বলা হয়নি, তো ভাবলাম এবারে বলে দিই। যাই হোক, ভালো করে এক্সাম দিস তোরা সবাই, অল দ্য বেস্ট, ওদের ভালো করে হোক। জানি না আমি নিজেই কি করবো, ইনহেরিটেড চাপ, ডিসার্টেশনটাও জানি না কতটা কি হবে। একটু তো এক্সপেরিমেন্টালি আমরা কাজ করেছি, কিন্তু ওরা যেমন চাইছে একদম ল্যাবে বসে কাজ তো আর হচ্ছে না, আর কোয়ান্টাম মেকানিক্স আর কি ল্যাবে কাজ করবো। যাই হোক, জানি না কতটা কি বোঝাতে পেরেছি, যাই হোক, ঠিক আছে, চল, অল দ্য বেস্ট ফর ইউর এক্সামস, গুড নাইট। তো